about the concurrency because, first of all, there's lots of opposition from within from MySQL development in terms of, hey, you're doing this, you shouldn't be doing that with MySQL. MySQL is not supposed to do that. And so we try to think in a bit opposite way because we already do that. And if someone is telling that application is not supposed to run to do 100 updates to a row, it's like, hey, maybe it's not supposed to, but we want to do 10,000 updates to a row a second. And we hit all these issues that on a server you cannot have more than 1,000 transactions, and because that will increase the cost of locking. So decrease the cost of locking, damn it! It's like we are not supposed to to have all these arbitrary limits when they can be eliminated in one way or another. And of course, sometimes when I was working for MySQL support before, we used to make a joke, like we should just publish a book out of the big comments and put it in the humor section sometimes. Like, of course, there are lots of insightful things, like it really well describes lots of things, how you design a database system, what kind of locking you have to do, what kind of, how you manage all the I/O back in year 95. So year 95 is 15 years ago, and I've been running MySQL for 10 years, and already, 10 years ago, you would kind of see that, a single Pentium machine with single disk is not somewhere you want to run your data, where you want to base your data center on. I know some people run Mac Minis in data centers, but it's not all kind of data critical deployments that like ours, like at Facebook or Wikipedia. So yeah, like we kind of try to educate, like Mark tries to educate, and we would like go and write the bugs and say, hey, this is the contention spot, we have to resolve that. And sometimes we get positive responses, and like it took years to get the faster crash recovery into 5.5 now, I guess, when there is the release at some point in time in future. So or lots of these things. Some of the stuff we just said we cannot live without it, and we end up having, like, when I say opposition from within, it does not include the MySQL support where people were like really helping and understanding our needs and then working on them internally. So yeah, that's the major thing. What comes into all these like concurrency scenarios is that we run on hardware. We have servers. Servers come with disks. Sometimes servers come with flash if you're looking to have lots of money, and then you don't have too many problems about the I/O, especially if you're using enterprise level solutions. But when you have disk, you have to understand that there are physics there, and it's like really fun to calculate that if a disk rotates 250 times, that's how many seats you can do. But the interesting thing there is that disks are scalable in terms of the more workload you put on them, more throughput you get at the higher cost of latency. And if like you take I took just a simple 16 disk box there, and I started like putting more and more workload, at increasing the threads, the number of threads like 16 times the number of disks, I could get nearly like that was nearly triple capacity, like throughput improvement. So whenever we have to think about all the workload that we want to put on the hardware, we have, like, in our case, it's not usually the CPU, because if you have efficient queries, if you have like well thought out like data access patterns, you don't really think that much about the CPU contention. You think more about how to access the data, and the data lies in disks. And so this is like one of the core things is the more workload we send down the hardware, better results we get us in terms of throughput when we're running lots and lots of queries, at least in theory. And we kind of try to approach that theory. Like, if we want to like really use our hardware properly, we can we really have to think that, hey, this is a request that a hardware can handle. How can we do less requests from the application per each data access, and at the same time how we can cram more and more requests into all these pipes that go inside our systems. I don't know, sometimes even the hardware can have all these crazy things, and tuning a bit there and there, like increasing, decreasing caches, can have quite fun results, which is kind of least like you always have to upgrade firmware and like your hardware firmware to get the best results of systems, because when they just were rolled out, not everybody did all the like benchmark testing. Like we just saw on a class of machines that if we actually reduce the write cache, it becomes much faster. I don't know how that happens, you should go and talk to all these like 60-year-old guys who write the firmware for that, but So again, it's like you can see a table here. I don't know how well visible it is, but at 128 threads, you increase like the time of each I/O by like 3 to 4 times, but you just scale out the throughput a lot. So it's like always when building like these systems, we have to balance between like low latency, high latency, how much throughput we get, and how far until the system just crashes down. And then there is another stack at the top. It's like everything that talks to the between the database and the hardware. And first of all, I don't know that well about ext4s. Like my disclaimer, I didn't test it too much. It's too new and had too many issues lately, so I kind of left it this high. But every other file system except XFS sucks. I mean, it's that simple. Like XFS has features others don't. Like XFS allows you to align data on the stripe boundary. What that means is that if you have this is the major source of misconception, why bigger stripe is better than smaller stripe. It's like on a bigger stripe, you'll have less of a chance to make the stupid mistake of placing your data on 2 disks at the same time for the same block. So by aligning your data and aligning your partitions, you end up having, instead of 2 IOs, just 1 IO. As simple as that. I mean, everybody should get it that easily. Only XFS gets it. 5 to 20% increase in throughput by simply aligning the data properly. The math is also quite simple. It's like if you have 16K blocks on a stripe, there's a chance that 8 blocks will be misaligned. Again, XFS is the only file system that can allow parallel direct I/O to a single file. If you have multiple files per, every table in separate file, probably will not be hit that hard. But if you have all the data in single table space, it's only XFS will allow you to have parallel write requests to a single file. And it's like, that's a kind of interesting contention spot. It doesn't always cause the trouble with efficient write-behind caching, but, well, when the battery is recharged and suddenly your write capacity falls down to like 1/20th of previous one, you kind of notice that. So it's like XFS allows like parallel flashing and way more operations to happen. And again, one of those simple things. Right, if you have a controller that can sustain, say, 15,000 writes a second, appending a file on such a like writing, you can do like 15,000 writes. Appending to a file on ext3 partition, ext3 file system, you can do like 5,000 writes a second to that file. That includes your bin logs, that includes any like logging data where you need synchronous writes. XFS already will do that at nearly 10,000 writes a second. That's like double the capacity of the industry standard file system. Now, if you actually try temporary file system, it will be twice as slow as ext3. I cannot explain that yet. I mean, I did a benchmark that, hey, in-memory file system twice slower than the efficient file. It doesn't work. But I mean, don't put your bin logs on temporary file systems. So the other thing is like, of course, Linux is fantastic. If you write a file, it's like you open a file, you write the file, you close the file. Linux will actually think that, hey, I'll buffer it a bit. Maybe someone else will open the file and write it something. So all these writes will happen about like 30 seconds after write, or sometimes in some cases even more. So if you have anything happening on your database system outside the MySQL D, all that stuff will happen at random things and at random performances and at random behaviors. Which is why any script that say compress this file with gzip, the problem will not be that you'll have CPU running there so something will take CPU. We have plenty of CPU, remember? Your queries are efficient. So the problem is that gzip will write a file, and operating system after like a minute will decide, hey, I have all this compressed data in memory. Let's flush me at maximum capacity I have. And of course, that will saturate the I/O, the database, it will saturate the write-behind cache, all the database operations will stop. So like, we really have to make sure that if you're running MySQL on a system, nothing else is uncontrolled and rogue behavior there, which is, you said, VM swappiness to 0, which like no swapping at all. Well, if you start swapping, you start killing people around who run software on your servers. VM dirty is like all these settings that control the flushing of data around. Make them as aggressive as possible in terms of like, whenever you see a data to write, write it. It's just don't buffer it more than for a few seconds, because Otherwise, we'll have all these like stampede writes coming to the I/O, while the database just, hey, I want to commit this transaction. Oh wait, there is someone just writing something. Again, we end up like pushing. Well, once you start like pushing your systems quite hard, every tool that is reading files on your system has to use like system calls like +XF advice to say, hey, I've just read data from your disk. Please don't cache that. And operating systems love when you start telling them, please don't cache that, because then they don't cache. And when you don't cache data, then there is no invalidation that will lock your system up for small amounts of times, like, half a second. And half a second might mean a few thousand lost transactions. So you kind of have to like always instrument pretty much everything where there's any larger memory operations or I/O operations on your machines to have, to not use memory and to use as least buffering possible. And if you're running on like really modern kernels, like not 2.4 or not 2.6.9, so there are some new syscalls in there that allow you to like sync file ranges and like do background things, like instrumenting operating system to flush data immediately. And this is what you have to do for like, or simply sync the file every time you write. So if you are creating a local file, just pipe it through DD and say, hey, sync every megabyte or so. Because you really don't want to see 500 megabyte writes coming to your file system while server's running. And this is one of those interesting things, like when you see that, hey, I have MySQL dump, which is creating a file, the usual problem is not that you're reading data from your server, it's that it's not that you're writing the data to the file system, it's that the operating system just delays everything and then just kills your system. Like it assumes you're running on a desktop, on a laptop. So it's kind of, you have all, and none of the server distributions are actually tuning this kind of behavior. And, last but not the least, whenever you see CFQ scheduling, kill it. CFQ is based on the concept that if you make a write to a disk, if it waits a bit, maybe you'll do a second write, which never happens with bin logs, never happens with the transaction log, because you were waiting for the first write to succeed, but operating system is waiting. Maybe you'll send it the second one. This can decrease your performance like up to 10 or 20 times on a reasonably sized system. So like, all these things, they seem to be quite basic, but it's like operating system will never do it well enough for you. You have to really take care of these things yourself. Sad. And then, MySQL basics is, lots of these things are, like, they look simple, but, thread cache, like how many thread, how big should it be? Like, usually just set it to max connection, so you're not taking that much space. Just, make sure the thread stack is not 8 megabytes. And still, it's even if you have all the thread caching out there, MySQL will not be fast enough to accept all the connections at the fast rate, which is at the web scale there is an issue. So always have in mind that MySQL has serious bottlenecks for actually like getting new connections in. The table cache and lock open is like, this is my most painful thing at the moment. It's every time, say when you're opening when you have say 1,000 queries a second workload running, and suddenly some query decides, hey, I need a table handler for a table, that hasn't been opened in the past half an hour. So what we'll do, it will serially do multiple disk reads from your disk to fill in statistics. It will read all the increment data, and during all that time, no other query will be able to start, because there is a huge global lock that's simply like every time you type select, it has to load the table list and so on, and that is protected. So while your system is reading those 10 writes out there from the disk, nothing else happens. So, the obvious way is, of course, just bump up the log table cache, and that will kind of help you. Well, the formula for table cache is the maximum size you need is the amount of tables you have times the maximum connections you want to serve. And the minimum is kind of the amount of tables you have. And then balancing in there is not that easy. And on the downside, there will still be a moment when you have to open a table in the middle of your high-performance production. So I hope to have patches for that, like by done my mark quite soon. But it's and again, like even if you have like large table cache, for some engines it will just fail at scaling, because it will be more and more expensive to maintain all these open files. So if you have single IB data, you can probably just increase the table cache to like 100,000 or whatever, because InnoDB just keeps the memory for all the open tables anyway in the dictionary cache, which doesn't get devoted. And there's MyISM, it's fast scans, not reads. So don't believe anyone who tells you that MyISM is faster. But if someone actually persuades you that you have to use MyISM, you have to then go and start tuning by using multiple key caches to be able to withstand the work. Because there's a single mutex guarding all the key cache, and it's so contended that after about 3 cores of use, it will fall down. And again, it's of course, right now, I guess the height is about 5.5. Last year it was about 5.4. But the current state of things is that if you want to run something in production, probably just 5.1 with InnoDB plugin is the good version to start. We're running still on 5.0 Facebook cache, which has actually backported quite a few things from the plugin and from Google cache. So you can grab Facebook cache sometimes. It's in really good quality. That I really love some of the features there, and I'll cover some of that later. And again, one of the things that once you open the Hype MySQL performance book and you look at it and it says, hey, if you want to set the InnoDB thread concurrency, try multiple values and that will work out somehow. So, I mean, even the best, kind of best sources out there that you can buy in a bookshop, in a bookstore, they don't tell you what it is, and it's quite difficult to tell what it is because it's a bit of a flawed concept. It kind of guards from the idea that if you have too many things running inside InnoDB, they will start contending and the operating system will not be able to manage that properly, and it quite often won't. And you kind of try to reduce the amount of work that is done by InnoDB at any time. The only problem, well, it's the major problem there that is it says, hey, just multiply CPU amount by 2, number of disks. But again, as I showed, the more workload you send to a disk, more throughput you get. So it's kind of, if default InnoDB setting says that you can run only 8 queries at the same time, they mean that 8 queries can be reading from memory or 8 queries can be reading from disk. And these are 2 entirely different problems out there when you're building a really concurrent environments. So what I see from our hostel is that we would like to have 2 separate variables, one telling how much concurrency you want on your disks and how much on the processor and memory. But unfortunately, it's not there yet, and we are still discussing how to better handle all these concurrency management situations. But at the moment, it's just, again, if you see heavily disk-bound workload, just bump up the thread connection, the setting as much as you can, or set unlimited. If you see lots of in-memory contention, you have to reduce. And then balancing that is exactly the art that nobody describes. So, but again, it's we have done some of the things. One of the major problems once you're running 1,000 queries at the same time, it is that all the concurrency management, it will say, hey, we have available concurrency slots. Can that thread wake up and start doing things? And the problem is that the Linux kernel and other operating system kernels, they don't make things immediately. So when you say, hey, I have a slot for you, come in here, that thread will just start yawning and looking around, doing some exercises before it starts running. So so what Mark did there is it's one of those things, how not to make things, we are not making things faster, we are not making them 3 times slower. So it's when you see that something is waking up at that time, try to understand that every operating system is in the has fuzzy states where you cannot just say 1 and 0, it's not running or not running, it's doing something in between. So while there are lots of threads doing something in between, Facebook has a patch that just allows more connections to come in and be executed at that time. And that just solved the problem a lot. So, there are these concepts that right now handle the concurrency. Some people think that it's entirely black box. It's not, but it's right now there are lots of changes being done to all these new MySQL releases, and Mikael is working and experimenting with that as well. But what we see is every different workload has you have to understand which kind of workload you're getting. And if you want low latency queries, you have to you can tune the concurrency tickets. InnoDB concurrency ticket is a concept that every time you read or write your own inside InnoDB, you consume a ticket. And by default, it's 500, which means that if you have lots of queries that they're doing like 400 rows a second, they will not go and be queued somewhere else. So the concept there is, if you want to make sure that you have plenty of queries that should happen in time, you should set the bit-thread concurrency tickets to amount of like 99th percentile of those queries, and remain the largest ones to be queued. And then, because usually it's the largest queries that slow systems down. And so quite often, if you have like web load, you will usually return in most of queries like 50 rows. So just set the concurrency tickets to 50 or 60, and then then you'll have like low latency situations for all the small queries and longer latencies for big queries. And it's like, again, that tuning is, once you get the idea of what a concurrency ticket does, it's way easier to modify the type of concurrency you expect from your system and the responsiveness from it. And the biggest problem right now for the current model is simply like, there are way too many cases when all these slots are held for something when they shouldn't. Well, if you're waiting for roll lock, it's not held, but disk I/O or waiting for commit to happen or all these things, threads are doing entirely nothing. But at the same time, they don't allow anything else to happen. And again, the DIO is like, as I showed in the previous quote slide, it's tuned for a single desktop machine with a single disk. It's not good. And there are lots of concepts there that they started fixing just now in the plugin, which was, of course, I was a happy user at Wikipedia of Google's patch for 4.0, and it was like one of the best releases I could ever get, because it just resolved all the I/O problems I had at the time. For example, DB does the read ahead in async. It's kind of the concept that you do some request, and database server might decide that maybe there is more data to load, so it just will do it in async. Now the async is just a background thread, single thread doing I/O serially, and all your 1,000 threads are pushing requests to that single thread, which is doing reads serially. So we have seen so many times those situations where anytime someone runs a query that reads more than a few blocks inside DB, it's like that immediately goes to async queue, and suddenly all the threads are stopping, and there's just one thread reading data. And it's not good. We used GDB to disable that at first. That was a cool hack that Mark found, actually. It was, if a server finds out that it's starting up, it will disable read ahead. So we just set a variable that, hey, the server is still starting up after a year of operation. It worked. So, and like, read ahead is such a huge contention spot. It's like, I saw recently that Flickr switched the database servers to like Percona build, and it's like, look at that, all the read ahead thing, all these pending IOs, they just dropped out. It's like, yeah, sure. It's like, I've said years ago, it's like, you don't use read ahead, that's it. Because, the concept of read ahead is, it's making one query faster sometimes, but it's making everything else slower because it's loading data. It's using the I/O. So if you have always stuff to run on your database server, you want only the things you need to be read. So just disable read ahead. Right now, I guess plugin has that setting. Of course, we have that right now in our 5.0 build. And it's like, it provides absolutely no benefit for highly concurrent cases. The single page flush thread is pain as well, especially for people who run on NFS or any other slightly higher latency I/O subsystems. It's just, whenever a server decides that it's time to flush pages, it has the many dirty ones, it will just queue them again to async thread, which will execute everything serially, one by one, which on NFS can mean, above a millisecond latency, when on local write behind cache you probably will not notice that half a millisecond latency or less. But still, it's, again, one of those contention spots that once you're hitting, it's painful, and that thread is also doing all the checksumming. So it's CPU operation plus I/O operation crammed together into single serial queue that is, well, not working that well as it should when you have more disks than one. And even with a single disk, as they showed, like the more concurrency you put on a disk, disks are quite complicated physical devices. They seek, but once they seek, they can read a track, and track has, there's a cylinder, and it can read megabytes of data or write megabytes of data in a single seek. So why bother with those single 16K write? And especially if you do a 16K write and then you have to calculate the checksum, the disk head has already moved away. So it's not that good. And again, flashing policies from 95, I guess I tried to remember right now exactly, but it wasn't that like, if there were at least 200 I/O operations done in the last 10 seconds, then the server is overloaded and we shouldn't do anything. Well, 200 operations, well, even if it's in a second, it's, right now we have servers that handle 100,000 operations a second. And of course what happens is like, as you don't do all this diagonal flashing, eventually you hit that point where it's mandatory because all other operations stall. So what you see is like, eventually, yeah, it's like, Jay was showing a really nice graph, it's like, at some point in time it's painful. So it's important, Google for all patch, have capacity, I/O capacity settings that simply change the constant and make things look much better. And right now, of course, Percona builds and then maybe plugin right now have these more adaptive flashing policies. So if you're running 5.0 still, or 5.1 without the plugin, sad. And again, let me repeat, concurrency slots are held during I/O. It's like if you want high I/O, you have to eliminate the thread concurrency model, and then you'll be hitting all the other problems, but well, at least you will have resolved this one. Ask your local MySQL sales guy to fix this. And the favorite part now is something what doesn't get, it doesn't seem that much in lab settings. Like in labs, people take sysbench and say, hey, run 1,000 threads against some table, spread out, uniform distribution, non-uniform distribution, and try to get metrics. I was like, what people do in labs, they don't usually take like these things what you would notice in production is like, how does sysbench go if you have 2,000 open transactions in your system? Or how would this go if you're updating a single row and it still has some locking overhead? And like, when we look at our production, we see lots of things that that are not kind of accounted or documented in any of these performance benchmarks that people do, and that means that they're not solved by developers because developers don't see the real world situation, they just look at the lab results. And InnoDB is painful sometimes. So InnoDB has this kernel mutex, which is held for anything like when locks are managed, when transactions established, closed, table opening requires kernel mutex, and so on. It's like, I've seen people say, hey, kernel mutex is not a problem right now. Well, it is. It's just sometimes hidden between lots of other things. And establishing like creating a transaction, you have to walk all the transactions to actually to understand what kind of data you should see, what you should not. It's MVCC database, quite complicated. And right now, of course, maybe there are some low-hanging fruits in their algorithm. We hope support will come up with an idea or Heike or someone, but maybe right now it's what we could do at Facebook, and we've been thinking that was in Mark's field, was maybe creating a new isolation level that is cheaper. And that is already like bending the database to our needs. Like we can probably change some of the semantics to make them implementable faster, because when people were writing all these ACID properties back in, or SQL standards like 10 years ago, 20 or 30 years ago, they probably didn't think that like people will be hitting these kinds of problems all the time. And block counts, right? So like InnoDB had a really nice behavior. Once I have 100 transactions waiting for a single lock count, the check for deadlock is exponential cost. So at a certain point in time, your server, all it will be doing, it will be checking for deadlocks and something where you usually don't have deadlocks. On a server that that has a deadlock once maybe every hour, we were seeing quite a lot of well, I mean, all the server was doing was searching for deadlocks. And of course, the first thing that we came up with was like, let's just disable deadlock check. Yeah, instead of updating 100 times or like 50 rows, 50 times that row a second, we just increased our performance to 10,000 updates a second by disabling something that is not working anyway and not doing anything. And we eventually hired some from MySQL support, provided a patch for that. It's better, but still in quite a lot of cases we have to just disable deadlock detection to be able to sustain with our workload. Because one deadlock check is going on, no, it holds kernel mutex, nothing else will be happening. And again, sometimes some of the things are just not visible. Again, in those lab benchmarks, when we have a transaction that suddenly updates 1 million of rows, or just does select for update on 1 million of rows, said, oh, I don't have anything to update, I'll release those logs. And while it is releasing those logs, there is probably some exponential cost there, everything else stops. So isn't, like, really the problem with InnoDB is that it's working for short-term things, it's working for like low concurrency cases, but it doesn't always resolve all, it's not always suitable for these high concurrency unless you start like really hacking things out of it. And again, I come back to the lock open. Major pain point is read statistics, reads auto increment information while opening a table and stops everything else, and even waits for kernel mutex, which means that the more, if there are lots of transactions and the kernel mutex is busy, then there will be someone will try to open a table, will have to wait for kernel mutex, and as opening tables stops everything else, you will suddenly have 5,000 transactions blocking on something, and then 5,000 first transaction will have to read the kernel mutex, which escalates into like a huge locking disaster and stuff just breaks. And again, kernel mutex in InnoDB is even obtained for it's waiting for a locked thread count. So we have lots of connect, disconnects. Some of InnoDB operations slow down. It's like all these things are just sad sometimes, but we have to come up with ways to fix that. So we have to to simply understand what is going on over there. So we have X thousand servers. Probably saw that at the keynote. So what we do there is we don't work on averages. Well, we look at averages to understand the growth over longer term, but for short-term analysis, we always go for like, give us top 10 servers by this property, give us top 10 servers by that locking, give us top 10 servers by row thread or threads running and so on. And once we have cherry pick servers to work on, it's way easier. And we even have a tool that is Dogpile. It actually has that's a logo for it. So it's kind of, usually it's like if you see an overloaded server, MySQL Enterprise Monitor doesn't scale that well for our scale, for our size, so we have to come up with something else. It's like, we collect information about servers, detailed information, only when they're overloaded. And like, we have, of course, lots of like long-term graphing abilities, but we have tools that fire when something like goes wrong on a server and just get us InnoDB status, IO stat, system information. Sometimes we just even put the poor man's profiler there. And it's like, then we can like really start working on the cases like what happened, why the server has that many threads running at the same time. Because like usually we don't want to have 1,000 queries running. 100 is kind of already a bit too much. So it's like we have a tool that collects that. We have also poormansprofiler.org. Again, it's a great tool. It allows us to see bottlenecks. Whenever something stops, we just run GDB, get all the stacks. Sometimes we freeze the server for 30 seconds, but if in the end it will allow you to remove hours of that locking state, it is very much worth it. It allows to see who is locking, who's waiting for locked threads, what are the locking chains. And once you see it, look at it, hey, look at that, it's right now it's releasing memory and internal memory allocation arena. It's like, yeah, apparently nobody looked at that, so we can just start working on it. Then the pile analysis is like once we see something. I don't think that this I'm using this in proper copyrighted manner. I should probably take down from my slides, but so worst cases are like you look at the pilots and you see what is happening. Like lots of rows scan. Hey, someone is writing bad queries. Or our problem is like when we have some memcached invalidation, suddenly we have X thousand of web servers connecting to our databases and suddenly running the same query, which is if we have a few thousand threads trying to read a few thousand rows, that's millions. And again, we can then immediately see what happened during a certain point in time and like And it's really simple. It's a small Python script, and you don't have to make it open source because anyone can write it in 5 minutes. But the idea is like just work on the top loaded servers at their top, at the peak moments, and then once you resolve problems there, you can just push all the changes to push all the changes down to like every medium loaded stacks and fix your averages with that. And of course, it's really interesting when you have not much of work going on, but the server overloaded, and then you have to really go to understand what is happening on what is being held. Because every time you stop and don't load your I/O to complete bandwidth, or don't load your CPUs, and you have stuff running, you have to fix that somehow. So the targeting, for us, targeting the worst of the worst has led to really fixing lots of performance problems we were seeing, and delaying big, wide disasters that would happen if suddenly your average server would have such properties. And it's in many cases people try to see throughput statistics. Oh, this query was running, there were 5 queries running over time. It's over time doesn't matter that much for us. For us, what matters is the workload interaction. And once we see what it's hey, if we have 300 queries of this type running and 500 of that one, it's way more information than just having the overtime numbers. And again, it's a poor man's evolution. Poor man at first had the show process list spam in the terminal window. This is a bit better, so we don't have to wait for this to happen. Yes, best performance debugger. That is the poor man's profiler. It's the tool that will be covered in lots of talks at this conference, I hope. But it simply tells you what the server is doing at any point in time. Run it 5 times, you will know what the server was doing 5 times. And you can make, 20%, 40% kind of figures out of that. But if a server is doing something really intensive, it will definitely show up at some point in time. It depends on how many times you run it. It's still, we kind of trying to put it to perfection, trying to figure out, kind of hack something out of GDB to make it lock the server for, under a second, not under a minute or under an hour. And again, understanding the workload has been the major thing for us to work to make all these, support hundreds of thousands of running queries. So put query comments in there. Well, Mark told that. We can use that. We can use that in TCP dump. We can use that in MySQL sniffer. We can use that in slow log aggregation. And the more stuff is there, hey, put the user ID, put the user IP, put the application he's using. And after a while, you can start aggregating that. Now, we added a feature to MySQL, which is called slocket. It is slow query log that goes to local datagram socket, which allows us to kind of attach custom listeners, and if they're not, their server is not writing to that socket, and as in, it's datagram. If stuff is not read as fast, they get discarded. It doesn't slow down the server too much. And we can actually, see all these, combine the low-level metrics you can see in expanded slow query log. We have actually added lots of additional metrics, per metrics to that, but we can have at high, we can do that for all queries. We can just have custom tools to do real-time. It doesn't go to a file, so it doesn't cause any I/O. We can do real-time aggregation and reporting based on that. And it is in Facebook patch right now, and it's a great feature. Managing the workload. Highlander doesn't have it, and a nice icon. It was invisible. It's the concept was hey, if we have all these thousands of queries running that come from a thundering herd, we should just kill all of them except the oldest one, because all the queries are going eventually to put the data into Memcache that will be used for the web application. So we don't really want 1,000 queries that would be putting data into Memcache at the same time to the same key. We just eliminate all the queries that are again, it happens at certain threads running threshold that most of you would probably say, hey, the server is dead by now. It's at 1,000 queries running, it was hard to scheduling the workload. So we eliminate duplicates. We probably sometimes, this desperate measure, will start killing longest running queries. And it's sometimes nice to see the graph of server being overloaded, then com kills just by making a small bump and suddenly the server is all happy. We even do something what is quite, we used to do that manually. It's if we see a server that is being really overloaded with lots of inserts and commits, we say, hey, set sync bin log to 20 and maybe disable the bflush commit, set to 2 or something like that. We just automated that because it's at a certain scale, it's a bit too much work to go and fix servers manually. But what it does is simply, whenever we see like hundreds of commits pending, we just unblock the, we just reduce the durability requirements for 2 seconds, and then we set it back when it all gets normalized. It has fixed so many issues with all of our, especially older hardware. And one of the features that I'm working now is like also managing some of the server settings, like max connections based on the type of workload that the server is getting. You don't want to have 5,000 queries at the same time sorting some data set, because that will simply run out of memory. But you probably can allow 5,000 queries or 10,000 queries sleeping there. And again, we have to do some desperate measures and like enforce application writers to start thinking about what they're doing for databases. You don't want to have 1,000 threads waiting for a lock. So what do? We reduce wait timeout, of course. We set, the lock wait timeout to 1 sometimes. Just, give an error to the web stack as early as possible. It will make them, like, they will see what they have to do about it. Because otherwise the query will just time out eventually because of the pile. And again, one of the critical things in high concurrency is like eliminate those concurrency settings. Like, give multiple applications their own IDs, set limits for them individually, so that if one application blows up, others are still working. And we use lots of memcache. It's caching is important, but in previous talks, I usually said, hey, memcache is overrated and databases is fast. Well, once you have that many web servers that seem to go to that one data, it's probably good to use memcache. And we cache everything. We cache empty data sets. If you don't get data, still cache it that you don't get data. If there's anything that you're going to repeat, just cache in memcache. Query cache doesn't scale for that, sorry. And then again, it's like, then have additional cache layer, put mutexes, add keys so that you have only one server reading for a certain memcache key at one time. So you avoid to have like, oh, key expired, they have a few thousand queries coming to the database server. That doesn't work that well at that point in time. So you have to somehow distribute the load or start locking at the application level, or at the memcache, create a lock key, and don't go to database all at once. And pre-cache the data instead of invalidation is also quite good sometimes. And the sad part is like caches still fail, and you still have to not to rely on it entirely. This is my favorite slide. Use stored procedures for scaling. I know it's not that popular in MySQL world, but what stored procedures do is they eliminate gaps between statements. And in a data center environment, in best case, you will see still half a millisecond gap between statements coming from a server that is not loaded at all to a MySQL server that is not loaded at all. It will be still half a millisecond waiting for a lock, like holding certain lock between 2 statements. So you have to eliminate that. And doing that is like triggers for us is like it's really from operations perspective, we kind of come up with an idea how to manage triggers, because we don't want DBAs to be in control of the data workflow. We want to just we can do schema change that will not change how application behaves. Triggers do change how application behaves. But stored procedures, they can be handled quite well from the application layer. And well, we don't use them at the moment. We kind of try to think how to better package it across, like, it's a big change application-wise. But, the thing is, if you have 2 statement transaction that updates one row, updates another, say, a counter table, and then commits, if you're not using, if you're having a consistent transaction, begin, insert, update, commit, you'll do like, what? On this slide, I guess shows 2,000 updates a second, like such transactions a second. That is the best case you will achieve on a local network with, like, servers out there. If there are any loaded, it will be spike way up. Now, you will be able to do maybe 100 or maybe 50 updates a second. Now, with a stored procedure, you can do 10,000 or like 12,000. Because you don't have any locking gaps in the state. They're like all your statements happen like immediately, and they don't blow up, and like the commit is not delayed by that additional millisecond that will just, a millisecond of locking is reducing the amount of updates you can do, just 1,000 updates a second. And one of the things that, of course, we had to do is we start to use intelligent proxies and intelligent caches that allow us to think of how can we merge requests, how we can make those writes Like if multiple clients are doing something, say increment a counter, we can just do a single increment instead of lots of them. And we try to reduce the amount of transactions because when it's sharded environment, the more servers you have, less statements go to same server. That means you're establishing more connections, and connections are, again, one of the major bottlenecks in MySQL right now. I hope it will change in future. And what we have to do is just, again, think of every way we can reduce that, and sometimes proxy is just the way to go to sustain such concurrencies. Especially if you have multiple data centers set up, because then you can add additional semantics for like when to roll back, when to keep running statements. Because if you do West Coast to East Coast transaction, it's 70 milliseconds of locking just in one round trip. It's slow, and if you know how to break the speed of light, tell us. No, I guess that's it. So again, we live at Facebook's page, MySQL Facebook. Kind of dominated by Mark, but we kind of add our comments and post stuff there that everyone else on the team. Yeah, I have also a blog that can be reached by the Bomas URL there. If there are any questions. Maybe not. I mean, I don't know how much time I have.
So the slide on store procedures, was that where you said statements? Is that client-side prepared statements?
No, statements were here, statements that were not wrapped in a transaction. It is just showing that it's locking impact. It's not the, so if you don't run the begin commit your statements when you are not covered in a transaction, they will not hold the locks, and so you will not be hitting the lock contention. The store procedure thing is just to avoid any kind of locking spans that slow down your whole application. Say if you have 50 million fans that want to be fans of a page that will give them free iPad if they look at certain photo. Well, I mean, there are lots of odd people there, but you have to think of these things.
Well, we cannot set it through it. So how can you test that consistent connection? Because in most times, everything that you're doing a connection for.
Well, of course, this persistent connection is waiting for 3 seconds.
Yeah. The database will have taken the time of the connection. So
well, if you're doing that transaction, you probably want to increase that for your session if you know that you're going to need it. If you're not going, if you don't increase that and you don't think you're going to need it, then well, you shouldn't be holding a connection. It's like really, it's about managing the workload all the time. Yes, Stuart?
Have you tried anything with selective read-ahead? So, for example, just doing read-ahead from like on the R&D in all scan, or just kind of like scan stuff?
Well, for us, the major thing is how do we make queries not need read-ahead at all? It's like the index only reads, do as few seeks as possible, because every additional seek is expensive. So, if you can think about selective read-ahead, you can probably spend that time on reducing the I/O.
Yeah, because I mean, the optimizers don't know when you use it on read-ahead.
Yeah, it's like, optimizing the query cache. It doesn't work eventually. So, Ronald? Oh, that was
Do you have much experience like playing around with like some of the settings that go with the optimizer and the depth that it goes in?
well, for optimizer settings, they're mostly for query plans. We are kind of usually sure that our query plans are correct. It's like, it's if you run a query that has to read this index and it doesn't read that index, you're screwed. But there are not that many settings, like in MySQL, besides the storage engine and a few basics that are that important. Yes.
How many active threads for server created?
You could do nothing to get the number of servers. Then I can't tell you that. Okay, I mean we see. So we used to run like at max connection 2,000. And we used to see, at peaks at overloaded servers running 2,000 maximum concurrent connections. Right now we increased max connections to 5,000, and we see 5,000 concurrent connections. So it's like, it's our worst cases are really bad. I mean, not all. I mean, if I go to work and I look at, hey, what are the worst cases that happen over past few days? I can have a bit of work to do. It's like, but it's well worth it because it just goes down to all the servers in the chain.
So you mentioned technique of using proxies to get connected to MySQL. So would that help your max connections in some ways?
Well, sometimes those max connections are taken by proxies. I mean, it's like max connections. Like we have to think like Idle connections, I don't pay attention too much to that because we have plenty of resources to support that. What we cannot support is connections per second established, which is proxies held, and threads running at the same time, which is what everything else comes with. Okay, you're just giving me out. Oh.